on chapter 13, equilibrium. And last time we talked about Kc, Kp. We also talked about, again, how you could go from one to the other using that formula that the Kp is equal to the Kc times RT to the delta N. We finished up talking about the idea of how to manipulate these sort of reversible equations. And if you need to do so, how that affects the value of the K constant. As we talked about, if you need to, in some cases, add a couple of reactions together, and you need to sort of figure out the K value for the reaction you get when you do that, you do multiply the K values together. If it's a situation where you maybe has to reverse a reaction, you then basically take 1 over K. That's essentially what happens to the K value. In some cases, you may need to multiply an equation by a common number, and how that affects the K value is you basically take the K value to that common number. If you multiply by 3, you would cube it and so forth. And lastly, the last way that you can manipulate some of these equations is to actually divide by a common number. And if you divide by the common number, you basically take the root of the K value to that number. So again, if you divide it by 3, you would take the cube root of your K value. The key is to sort of keep track of what you need to do, how the K values sort of change, and then you can get the overall K value when we're all done. Any questions on that stuff there? Okay, so why don't we try one? I think that's sort of where we left off. So let's say we had these two reactions here up on top. And we're looking to basically figure out what it would be the K value for the reaction on the bottom there. So why don't you take a couple minutes and see what you come up with. Again, we want to kind of manipulate the top equations to build the bottom equation, and obviously keep track of what we do to our K values here. So take a few minutes and see what you come up with. All right, let's take a look and see how you're doing. So again, in these cases, the best thing to do is just to kind of get everybody on the correct side and make sure you have the right amount of everybody. So for example, here in the first one, I see A and B on the left, and the final reaction that equation that we're going for, A and B are on the right-hand side. So clearly I need to reverse the top reaction. In addition, I don't just have 1 of A in the final one, I got 2 of A, which means I also need to basically multiply that entire first guy by 2 as well. So if I do that, I end up with 2C plus D, 2D, goes to 2A plus 2B. Now, the importance here is to sort of think about what that does to our K. So clearly, when I reverse it, it then becomes 1 over K, right, as I reversed it. And then I multiplied by 2, which means I then need to square it, right? So that's basically all the manipulations that we did on that first one. So putting that number in means that essentially we got 1 over 25 squared would be the proper K value for that one, which would get us, and do a little squaring of it there, gets us a 0.0016 for the proper one. For the second equation, I need 2 of E and D, which I do have, but again, E and F are on the wrong side. So E and F needs to be reversed. So the second one, we need to reverse it, and that would get us 2E plus 2F goes to 2C plus 2D. In this case, all we did was reverse it, which means we would just take 1 over K, which would be 1 over 5 in this case. And that would get us 0.2. Now, to make sure we did this right, we want to add these together. In this case, the 2C's cancel, the 2D's cancel. And that leaves us with 2E plus 2F gives us 2A plus 2B. That means we did get the right equation here. At this point, to get this K, right, we would we do have to multiply them. So not adding, we wouldn't multiply them here. which would be 0.0016 times 0.2, and we'll call it like 3.2 times 10 to the 1, 2, 3 minus 4, it looks like. Any questions on any of that? So as I think we talked about last time, it's very similar to, if you remember, sort of Hess's law. The key here is a few different things occur to the equilibrium constant when you manipulate these equations. But really the key is just to sort of keep track of what you did so that you could adjust, obviously, the K values correctly. And then the very common mistake at the end here is when we do add them together, we're multiplying, not adding. So it's a very common error that people make. Any questions on manipulating equations or anything like that? Okay. All right, so as we talked about in terms of the equilibrium expression, typically we do express everybody in concentration or molarity. As we also talked about, you could kind of do it in terms of pressure, right? Like a Kp. Remember that when you kind of do any of these equilibrium things, these are really the standard units that you want for solution to be in molarity, and pressure there to be atmospheres if you're dealing with any type of gases. As we talked about, solids and pure liquids will have no effect on the equilibrium, so they are never included, which, as we talked about, basically means that's aqueous and gas, which are included. The equilibrium constant, again, is just a number, which does give us some idea as to when this reaction reaches equilibrium, what we mainly have. Do we mainly have reactants? Do we mainly have products present, based on sort of the number that is there? And when we do see an equilibrium constant, it is constant for the actual reaction or equation that you're looking at. It is specific for that temperature. And a couple of things that we talked about was that you can, as long as you keep the temperature constant, you can start with various amounts of reactants or products in an equilibrium reaction. It will always end up with the same equilibrium constant. The only actual thing that will affect the value of the equilibrium constant is temperature. So if you change the temperature, the value of K technically will change as well. If we do some of our manipulations here by either adding them together, we want to multiply, and then obviously what we just talked about there, if we reverse, we take 1 over the K. If we need to multiply by a common number, we take it to that power. And if we need to divide by a common number, we obviously take it to that root. All right, so K, as I mentioned, does have the same value, regardless of what you start with. And again, as I talked about last time, that is a very hard concept for people to think about. They think about a lot of times, you know, I started with way more reactants in this run than I did in the first run. I should end up with a different equilibrium constant, and that's just really not the case. You will end up with the same ratio of products to reactants when you do calculate the equilibrium constant. All right, let's talk a little bit about another letter here briefly, which is Q. Q is what is referred to as the reaction quotient. And excuse me, Q is calculated the exact same way as K. So it is exactly the same. It is the concentration of our products using the coefficients as the exponents, just like we do with K, over our reactants, same deal, using the coefficients as the exponents. So you may say to yourself, if Q is basically the same as K, or calculated the same as K, what is the difference between them? We use the reaction quotient, or Q, to help us determine a couple of things. In a basic sort of Q problem, if you will, the question is usually this: are you at equilibrium? And if you're not at equilibrium, which way you need to go to actually reach equilibrium? So we use Q typically when we are not sure we're at equilibrium. We have initial concentrations and we put it in, and it helps us decide, first off, are we at equilibrium? And again, if not, which way we need to go to reach equilibrium. If we calculate Q and it is greater than the K value, that means that the reaction is not at equilibrium. And in order to reach equilibrium, kind of opposite of where this is pointing, it needs to go to the reactant side to reach equilibrium. We need to make some more reactants. If you calculate Q and it actually does equal the K value, then you have a system that is at equilibrium at this point. And lastly, if you calculate Q and it is less than the K value, tells you you are not at equilibrium. In order to reach equilibrium, you need to head towards the product side and make more products. Now, clearly, because Q is products over reactants and is calculated the same as K, in order to be able to calculate Q, you do need everybody's concentration or pressures. Obviously, if they are not given to you, there's no way to calculate Q. We will see Q pretty much in a couple of places. One place is, like I said, just really kind of like a straight problem, a Q problem, where they want to know, are you at equilibrium, which way you need to go to reach equilibrium. Later on, when we calculate sort of equilibrium concentrations, Q can pop up in that situation as well. So whenever you're sort of given the starting amounts of everybody, you're not sure if you're at equilibrium, you know, that's a good idea to calculate Q. So why don't you try one here? If we start a reaction with 0.249 moles of N2, 3.21 times 10 to the minus 2 moles of H2, and some NH3 there in a 3.5 liters. The Kc is 1.2. Is the system at equilibrium? And if not, which way does it need to go? So take a few minutes, see what you come up with. And to really calculate Q, it's the exact same way as you would do K. So if we were to write the expression for Q, it would be our products, which would be the concentration of NH3. Just like Q, we would need to square it because of the coefficient. We would divide it by the concentration of N2 and the concentration of H2, which we would again have to cube in this case. In this case, it gave us moles and liters, so we do need to kind of convert everybody into molarity here. So the concentration of N2 should be 0.249 moles divided by 3.5 liters. And that would get us divided by 3.5, call it 0.0711 molar. We could do the same thing here for H2, which would be 3.21 times 10 to the minus 2 moles per 3.50 liters. And that gets us, looks like 0.00917. And lastly here for our NH3 would be 6.42 times 10 to the minus 4 moles divided by 3.5 liters. Gets us 0.000183 molar. At this point, we have all of our sort of initial concentrations, put it into our Q expression, our NH3, which is 0.000183. Again, we want to square it, divided by our N2, which was 0.0711, and our H2, 0.00917, which we do have to cube in this case. That's going to get us 0.000183 squared divided by 0.0711 divided by 0.00917 cubed. Looks like it gets us a Q value of 0.61-ish there. Any questions so far on that calculation? At this point, what we want to do is take our Q and compare it to our K. And in this case, we see that the K value is 1.2. Our Q value is 0.6, which means in this case, Q is less than K. That tells us that we are not at equilibrium. And which way do we need to go to reach equilibrium? Kind of opposite of where it's pointing, so we need to head towards products there, basically to reach equilibrium. Any questions on Q here and how to calculate Q? Again, really, like I said, same as K. We use it a lot to basically answer those two questions, sort of if we're at equilibrium and which way we need to go to reach equilibrium. is typically what we kind of use Q for. Any questions on that there? Okay, then let's talk about really the calculation of the season here. And the calculation of the season here is solving for equilibrium concentrations. And to solve for equilibrium concentrations, we use what is referred to as ice tables. And maybe you use ice tables in Chem 50. Sometimes people will do it when they are talking about limiting reagents. Anyone? No? No, they don't teach it all that much anymore. They should, because it'll help you when you get to this class, but they don't. All right, so we're going to use ice tables to help us do this. And whenever we're given really the initial concentrations and we want to figure out what's going to happen to the concentrations of everybody when they do reach equilibrium, we do use an ice table, and ice stands for initial change, and E is equilibrium. So this is pretty much the calculation that we use all over the place in this class. And it's a really important calculation to understand and do correctly, as it will constantly keep coming up, these type of calculations. So in a problem, like I said, typically we're given initial concentrations. Using the initial concentrations and an ice table and the equilibrium constant, we could actually calculate basically what the equilibrium concentrations or pressures would be when everybody reaches equilibrium. It is math, so we do want really just one sort of variable. So the variable that we typically use is x, and x represents really the change part of the table. So we kind of use x to represent that. And then mathematically speaking, we go and solve for x. And there's a couple different ways you can solve for x, as we will see. The probably most difficult way that we will solve for x is to use the quadratic. That is something like ax squared plus bx plus c, right, is equal to 0. And that is like x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Good memories of math coming back right about now. Yes, prior bad memories, whichever way that is for you. So this will be probably the most difficult way that we will solve a problem here. There's other ways that sometimes people use successive approximation, which we won't do in this class, because if you're crappy at it, you'll be there all day trying to solve the problem. So the quadratic would be the hardest way. And let's take a look at one here together and work through it so we can kind of see, you know, how it all works. We'll hope for the best here. All right, so at equilibrium, the equilibrium constant for this reaction here is 7. If the initial concentration of Br2 is equal to 0.663, calculate the concentrations of the species at equilibrium. So where we want to start with is really our ice table. So we usually will take the equation here. And we will initially put what was given to us, which in this case is 0.663. Now, in this case, in a lot of problems, we sometimes are not given anything on the product side. And in those situations, it's pretty much safe to assume that you are starting with 0. So it's very safe to sort of assume that. The change part is where we do the x, and a couple important things. In a situation where we sort of assume 0 for our products, we would expect this reaction then to be heading in which direction? If we have no products, it should be heading in the product way, right? So it should be going towards products. That means as time goes by, would we expect more or less reactants in this case? Which have less. So that's represented in the ice table as minuses. Products, we would expect more to be made, right? So that is represented as pluses. So like minus x's plus x's. So the other really important part of the change part is everybody's other favorite thing, which is stoichiometry. Yeah, mole to mole relationship, all that good stuff. So when we do the change part here, we would say minus x, because the coefficient here is technically 1. So that's like a minus 1x. The coefficient here, though, is 2. So we do need to take that into account here. Otherwise, you just screwed up the mole to mole relationship of this calculation. And we would represent that by plus 2x in this case. So it's really important in the change part to take the coefficients into account, because really when you do that, it is taking care of the mole to mole relationship, the stoichiometry for you altogether. If you don't do that, then you pretty much screwed up the calculation here. The equilibrium part here, we're just going to carry it down. That's going to give us 0.663 minus x and 2x. Any questions so far? We could also write our equilibrium expression for this reaction, which is the K is equal to the concentration of Br squared divided by Br2, and that's going to equal lucky number 7, right? Let's talk about the ice table here for just a second in units that we sort of talked about a little bit earlier. It is this situation here when you are doing ice tables, your concentration should be molarity. And if you have pressures, it needs to be atmospheres when it goes into the ice table. So again, you could do this with like a KP and pressures, but it definitely, as we talked about earlier, needs to be in atmospheres. Even in a problem where they give it to you, like I said earlier, in TOR, and they want the answer in TOR, when you go into the ice table here, it does need to be in atmospheres in order for you to do it correctly and then sort of convert at the end. The goal here now is really to solve for x. So what we're going to do basically is take everybody there on the equilibrium line, and we're going to stick it into our equilibrium expression. So if we do that, that gives us basically 2x squared on top, divided by 0.663 minus x on the bottom is equal to 7. At this point, we need to get everybody kind of combined, all the same x's together and everybody to the same side. That means mathematically speaking, I need to take what's on the bottom there and multiply it to the other side, right? So I got to take everything over there. I'm going to also take care of the top as well. So the top there is going to give me 4x squared. Taking everything to the other side there will give me something. It'll give me 0.663 times 7 gives me 4.641 minus 7x. Now, I am now going to bring everybody to the same side, and typically this is shaping up very quadratically here, yes. And typically most people keep the x squared positive. You don't have to, but most people keep that x squared part positive. So that means I'm going to bring everybody on this side over to the other side. And that's going to give me 4x squared plus a 7x minus a 4.641 is equal to 0. And that is basically my quadratic there. That is my A, B, and C in the quadratic formula. Any questions on that so far? So we are going to go into the quadratic formula, which was that guy that I showed a second ago. That is x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. By the way, when we use a quadratic, we end up with how many answers? 2, yeah, so we usually end up with 2 answers. All right, so putting this in here, we got b, which is, b is our 7, I believe, so that's going to be minus 7 plus or minus, and I'm going to take care of the square root part inside. So that is b squared, which is 7 squared minus 4 times a, which is 4 in this case, times c, which we do want to keep the negative 4.641. That gives me inside the square root about 123.256, which when we do take the square root of that, yields me about an 11.1 when we do take the square root of it. That's going to be divided by 2a, and I believe a was 4, correct? So that's going to be 8 on the bottom. Any questions on that there? That now will give me, again, 2x values when I do that. Again, doing the positive followed by the negative. So we'll do the positive one first there. So that's going to be minus 7 plus 11.1 divided by 8. Gets me a 0.513, we'll call it. Or if I did the negative, that would be negative 7 minus 11.1 divided by 8. Gets me a negative 2.2625. Any questions on that so far? So when you do the quadratic, you obviously will get 2 answers, and one of the answers will not make sense. But let's talk about what these x values are. Going back to our table, the x values that we just got are all the x values in the table at the equilibrium line and all through the table here. Which x value would not make sense here? It would be the negative one, right? If I put the negative 2 point whatever it is in here, I end up with a concentration of like -4. Can you have a negative concentration? You cannot. So in this particular case, the negative does not work when we put it back into the equilibrium line. And that is typically what will happen when you do the quadratic. One of the x's you put back into the values in the equilibrium line will not make sense and give you like a negative number, and that obviously is not the right one. That means I'm going to roll with this guy here, which means we're going to take that guy again and put it back into our equilibrium line. So that is 0.663 minus x. So that is 0.663 minus x, which would be 0.513. And that gives us a concentration of, hit my calculator right there, we go, 0.513. 0.663 minus 0.513, there you go. Gives us a 0.150 molar, and that was for Br2. For Br minus, I believe that was equal to 2x, which would be 2 times 0.513. And that would get us 2 times 0.153. About, I'll call it a 1.03 molar there. These would then represent, as we can see from our ice table, the equilibrium concentrations of these guys. Actually, it's just Br, no minus, of each of these guys here. Question on those steps. Now, this is math, right? Which means we could actually check ourselves to see if we didn't screw up somewhere. This was not a very difficult quadratic sort of deal, but some of them get quite difficult in terms of factoring and stuff like that. How can I check to make sure I didn't screw up? These values that we just calculated are the equilibrium concentrations, right? Which means if I put it back into my equilibrium expression, I should end up with what number? About 7, yeah? And if I do that, I do get approximately 7, right? So that's a good way to check yourself, make sure you didn't screw up, because like I said, a lot of times there's a lot of places where you can screw up. And again, if you put it back in and you got like an equilibrium constant of like 400, definitely you screwed up somewhere in the math part of it. Any questions on the ICE table? Super important calculation, like every calculation for the next 40 months will be this one, yes, or a variation of this one. You can't go wrong usually in this class if you throw down an ICE table at this point, yes, so it's a good thing to kind of do. Any questions? All right, so we will lay it up there and do just nothing but ice tables next time when we come to the lecture, and we'll do a bunch of different examples of these guys and different ways to solve for X and stuff like that.